Tonight, we really begin to investigate a type of motion that gives us clues to the workings of the universe, from the very, very small to the insanely large. Accelerated motion! That's right. You can, well, you can't because it's covered up, but our main goal tonight is to be able to recognize accelerated motion and be able to define acceleration. But first, a reminder. As useful and awesome as these videos will be, don't forget an important resource for your learning is always your textbooks. Don't forget to look at 3.1 and see what they have to say. But first, what is accelerated motion? How about some examples? Ooh, there's some acceleration. Look at that thing go. Ooh-wee. Acceleration at the beginning. Acceleration at the end. Right. Before we get into this, let's look at non-accelerated motion, uniform velocity. We see here this brave young man moving forward, never changes direction. Every second he has the same displacement, which means he has a constant, come on, you know the answer. That's right, a constant velocity. As he progresses forward, he has attempted to drop a single drop of food coloring on the paper towel every second. We recorded the position of each drop of food coloring to effectively make a particle dot diagram. We then use this to construct a position time graph and a motion diagram. Well, we tried to get one drop per second. It didn't always work out too well. Let's take a look at the motion diagram and the position time graph as well. Now in the motion diagram created by the releasing one drop of food coloring every second, you can see that the displacement between each image is almost exactly the same. Not the first second where your hands start moving, but with each preceding second. Notice the displacement, and the displacement's the same, so the space between each image is the same. If we look at the position time graph, we see that we virtually made a straight line. Not exactly, but the line of best fit is clearly a straight line. And that's really easy to find the velocity of simply by calculating the slope. I can just choose 2 points. There's 1 point there, and I'll choose this here. I can see the rise, the run between those 2 points. I have positive displacement. In this case, it's gone about 2.0 meters. And if I look carefully at the run and check against my scale, I'd find it's 1.8 seconds. So 2 meters divided by 1.8 seconds, and that's my velocity. So that brave young man was going about 1.1 meters per second. Now we see me making a motion diagram, and ooh, look at me go! Again, we recorded the position of each drop of food coloring and used it to make a motion diagram and collect the information for position time graph. Of course, this time you could clearly see I was doing accelerated motion. I was going pretty fast. Not at the beginning. At the beginning, I was going about the same speed. When we take all this data I collected and we start looking at it, and there's me. I hope that's not anatomically correct. And my beginning point. Okay, I start out really no different than preceding man. In fact, a second later, I haven't moved. By time 2 seconds, it seems the same. Oh, whoa, here's the difference. We can see both in the motion diagram, a huge increase in spacing. And then look at the position time graph as I point. I'm already off the graph. I've only made it to about 4 seconds and I don't have any more space. Clearly not a straight line. My line of best fit in this case would be a parabola. This is accelerated motion. It doesn't make a straight line. No straight line. However, I don't want to leave you with the wrong impression. Acceleration could also cause slowing down if the acceleration is against the direction of the velocity. It's against the velocity. That's called negative acceleration. Important to know. Go for a jog, but just take it easy, okay? Nothing too crazy. Okay. Nice and light. All right. Positive acceleration. Positive acceleration. Positive acceleration. Negative acceleration. Negative acceleration. So acceleration could be any change in speed, both positive or, unfortunately, at the end of that race there, it could be negative. It could be working against my direction. It's easy to see this in motion diagrams because the displacement between each image or particle dot is no longer the same. Spacings be quite different, in fact. Like, for example, I hate to relive a painful memory, but let's take a motion diagram of the race you just saw. You can see at the beginning we were taking it easy as promised, but then when David started to pull ahead of me, I couldn't stand for that. So we can see acceleration. There it is, your first sign of acceleration. Quite a big space. More acceleration. Look how the displacement has continued to increase, therefore the velocity has increased. Oh no, that's not good. That's probably where the garbage cans were. So a huge change in displacement. And that's what happens. All right, so let's test this out. I know you can't read the question, so I'll read it for you. Which motion diagram below shows absolutely no motion at all? Nothing, no motion. A, B, C, or D. See if you can think of it. Come on, shout it out before I circle it. I'm going to circle it. Oh, you're too late. Yeah, that's A. In spite of each second going by, we don't see separate images. It's all the same superimposed. All right. Which shows uniform velocity or non-accelerated motion? A constant velocity. Which shows a constant velocity? A, B, C, or D? Good options here. Good. Of course, B. But before you would move on, if this was a Minds on Physics, you'd have to pause and realize, well, wait a minute. 0 meters per second, that's constant velocity. That's not moving. So both A and B. Let's move on. What about accelerated motion? Which of these motion diagrams shows accelerated motion? Very good. Wait a minute, that's me, but I'm proud of myself. I hope that's not the only one, though, because what we just saw in the movie is we can have negative acceleration, so both C and D. We could also show this as a change in vectors, but how do we do that? How do you use vectors to figure that out?
Why, that's easy.
Well, here we have Mr. Universal Stickman running forward, and clearly he's speeding up. So I'm going to look at Mr. Stickman again in 1 second increments, and we can see I've added the displacement vectors in green. And I'm also adding the velocity vectors, which are the same, not only because, of course, velocity is proportional to displacement, but it's per second. So each of these is my velocity. Now to find the acceleration, here's where the vector subtraction comes in. I can take a preceding velocity vector, reverse it, and the difference between them is my acceleration vector, shown in violet here. So now I'm adding not only my, of course, displacement and velocity vectors, but I'm adding my acceleration vectors. I'm going to do another vector subtraction here. Took the preceding velocity vector, reversed it, put it against the other velocity vector, and we see the difference. And so that's how we can use subtraction of velocity vectors to find out the acceleration, create acceleration vectors. So let's take another look at my ill-fated run using this technique. So acceleration is really a change in velocity per time. By vector subtraction, we're showing it's your final velocity minus your initial velocity over time. So the units will always be speed per time or velocity per time, like meters per second, meters second squared. Or for dimensional analysis, it might be easier to do a meter over 2 seconds. All right, so here's a problem. Which of these following could be units for expressing acceleration, even if they're not appropriate SI? You may want to pause for this. Pause it. Solve it. You didn't pause. Pause it. Pause. Yeah, it is a trick question because all of these are speed units, meters per second, miles per hour, kilometers per second over time. All right, so which would be the correct SI unit for expressing acceleration? You may want to pause it. Here it comes. Right, we already know meters per second is correct for velocity, so let's re-ask some of these questions with this new data or new expressions, like this one. What's it going to be? Hurry up, the answer's coming. A, B, C, or D? Oh, come on! Well, what are they saying? 0 meters per second means no motion. So I asked this exact same question before. 0 meters per second squared means no acceleration, so non-moving. All right, how about a person moving 4 meters per second with acceleration of 0 meters per second squared? Well, I asked that before. That's the uniform velocity. What about positive acceleration? Come on, you can do it. We had this question before as well. But only positive this time. We should see the displacement increasing over time because the velocity is increasing over time. And there it is. The acceleration vector is in the same direction as the velocity. What about 3 meters per second with an acceleration of 0.8 meters per second squared? Well, wait a minute. That's positive acceleration, right? It's going in the same direction. So it's the same question, which shows negative. What would be negative acceleration? Good. But suppose I phrased it this way. Velocity 5 meters per second with an acceleration of negative 0.8 meters per second squared. Yeah, it's the same thing. So don't let that throw you off. So remember, acceleration is change speed. It's also change in direction. Don't forget that. Here's, for example, 6 lab quests. Are there any accelerated motions in these lab quests? You see a lot of straight lines, but you notice these two were the lines of change going from non-motion to motion back to the origin, or motion away from the origin and stopping. That would actually be accelerated. And so now for today's really tough question of the day. I'm not going to solve it for you. I'm just going to help you get it set up. Watch the time increment of each of these photos. It's very fast strobe light. I'll go ahead and get these vectors in place for you. These are velocity vectors, not per second though. Notice too to the left, that 0, 10, 20, those are actually millimeters. So each one of those would be a centimeter. So this 10 that you see here, and the 20 and 30. So watch that. Let's see if you can solve that. Use vector subtraction to figure this out and bring it in. Have a great night.